This is Forces Lesson 10, and this is momentum conservation. It can be quite a tricky one, students struggle with this a lot. So the objective of this video is to make conservation of momentum calculations. So what is momentum conservation? Remember to pause at any point if you want to make any notes. Momentum is conserved in any collision or explosion, provided no external forces act on the colliding or exploding bodies. It's a bit convoluted, it seems a bit strange. Essentially, so the GIF below can help a little bit. So essentially, two bodies will come into contact in a straight line. There's no external forces acting on them, so there's nothing pushing them from the side or anything like that. And essentially the momentums will kind of add together. My boots are pretty good, by the way, but I'm going to turn notifications off. So basically these, the momentums kind of add together, and the momentum will transfer into one of the bodies more so than the others. It helps to do it mathematically. So I'll do an explanation like a question. So I'll show you how it works, how to set it up, and then we'll just do some more questions until you're comfortable doing them. Okay, so let's have a look at the first one. So in this one, a truck of mass 0.5 kilograms moving at 1.2 meters per second collides and remains attached to another initially stationary truck of mass 1.5 kilograms. Calculate the common velocity of the trucks after the collision. So there's a nice way to set this out. So I'll show you how to do it, and then I'll show you how to answer the question. So let's have a go at this one. So what you should do first of all is kind of divide the screen up. So there should be enough room. And what we want to do is look at the momentum of everything before the collision and then the momentum of everything after the collision. So I'm just going to write before and after. Okay, so before the collision, so we need to do the momentum of everything. So let's do the momentum of truck A first. So that's 1.2 times 0.5, so it's just mass times velocity. So I've not calculated. You can calculate that because obviously it's very straightforward. Sometimes it's not, so we just write the sum out, plus, and this one's 1.5 times 0. Obviously that's 0. And then so that's before, and then we're going to do the momentum after. So we put an equal sign in the middle. And then we do the momentum after. So what happens is it says that the trucks have collided and they remain attached. So if they remain attached, that means we have the combined mass of these two trucks. So that's the mass is 2. And the velocity v is some unknown common velocity that they'll have. So we need to times that by v. Then it's just some simple maths. So we've got 1.2 times 0.5. So half of 1.2 is 0.6. Equals 2 lots of v. So we need to make v the subject. So we need to get rid of times 2, which is divided by 2. So 0.6 divided by 2 will equal v. So v, the common velocity of the trucks after the collision, is equal to 0.3 meters per second. You'll notice that in the center, the equal signs only go in the center line. I would advise whenever you're doing a question like this to make a table like this. So what you can do is, if you want, is to make some notes, rewind, do the question again and see if you can get the same answer. But I'll move on and do a different example. So in this one, it's going to be the same technique. As you can see, I've got pretty good at drawing straight lines. Right, so before I've not even read the question yet and I'm still setting it out. So it's the momentum before the collision is equal to the momentum after the collision. So we can safely say that before is equal to after. Obviously it's momentum. So let's read it. So a train wagon of mass 8,000 kilograms moving at 4 meters per second collides and remains attached to another wagon of mass 12,000 kilograms that is moving in the same direction at 2 meters per second. Calculate the common velocity of the wagons after the collision. So this is the exact same question as what we did before, aside from initially the second wagon is also moving. So if you want to pause and have a go at that, that's okay. If you don't, or you want me to show you, or you're ready for an answer, I'm going to do it now. So we've got a train wagon, so we've got 8,000 kilograms for the first train wagon, multiplied by its velocity of 4 meters per second initially. Plus, then we've got the second wagon that's got a mass of 12,000 kilograms, and that's moving at 2 meters per second. So that's the momentum of both of the objects before the collision. And that's going to be equal to the momentum after the collision. So after the collision, they remain attached. So we have to combine the masses again. So it's 12,000 plus 8,000, which I believe is 20,000. And then we're going to calculate their common velocity. So we need to times that by v. So if you didn't get that far, now it's set up. If you want to finish that, that's okay. So 8,000 times 4 is 32,000. Plus, and then 12,000 times 2 is 24,000. Equals 20,000 times v. So I'm just need to add these up on the left hand side. So we've got 56,000 equals 20,000 v. And then we just need to make v the subject. So we need to get rid of times 20,000, so it should be 56,000 divided by 20,000. Hopefully you got this okay. Let's check the answer. And that will give us 2.8 meters per second for the common velocity after the collision. So hopefully you found that one all right. Let's move on. So we've got one more question for you to attempt. So a car A of mass 1,800 kilograms traveling at 10 meters per second crashes into the back of another car, car B, of mass 1,600 kilograms traveling in the same direction at 4 meters per second. The cars come together and move down the road. Calculate their common velocity. So if you want to have a go at this one, you know, similar to the ones we've just done. Hopefully you're getting the hang of this now. And then I'll take you through the answer. So here we go. Right then, so the momentum before the collision, hopefully this one's gone okay this time, is equal to the momentum after the collision. That's the conservation of linear momentum. So the momentum is conserved, so it's the same before as it is after. So let's just do the momentum. So car A, so we've got mass of 1,800 kilograms, and it was moving at 10 meters per second, plus the momentum of the other car, which has a mass of 1,600 kilograms moving in the same direction at 4 meters per second. And then they come together, so the masses will combine to 3,400 kilos times v. Then it's just some maths, just like last time. So we've got 1,800 times 10, which is 18,000, plus 1,600 times 4, which is 6,400, equals 3,400 lots of v. So let's add these together. So we've got 18,000 plus 6,400, which gives us a total of 24,400 equals 3,400 v. So you should be getting the hang of these now. So we just need to do 24,400 divided by 3,400, which gives us a combined common velocity of 7.2 meters per second. Hopefully that final one went okay. Let's finish with a closed exercise, just as a consolidation. And here it is. If you want to try it, you can pause it now without any help. If you want the keywords, I'll put them on now. And then in a few seconds, I'm going to take you through the answers. So the momentum of an object is equal to its mass multiplied by its velocity. Momentum has direction, the same as the velocity, and is measured in kilogram meters per second. In any interaction of bodies where no external forces act on the bodies, momentum is conserved. In snooker, for example, a head-on collision of a white ball with a red ball can result in the red ball moving off with the same initial velocity of the white ball. This is an example of momentum conservation. And in the next video, we're going to look at head-on collisions and explosions. So I hope you found that helpful. Thanks for watching, and I'll see you at the next one.